So hello friends, welcome back to my YouTube channel. In this video we will be discussing the discussion of advanced experimental designs. I will create a playlist explaining the lecture notes line by line. Now we will start with analysis of variance, which is ANOVA, that we are already familiar with, right? So this is ANOVA. First we have to understand what ANOVA is. Here ANOVA is a statistical method used to determine if there are any significantly if there are any significant differences between the means, right? So here I have highlighted the word means because here we will be checking if there is any differences among the means of different groups, right? More than two groups, okay? So of three or more independent groups, and the group should be independent, right? So when we perform ANOVA test, we don't consider before and after scenarios. Before after scenario we don't consider, right? So they are independent, right? For example, if you take group 1, or we can say fertilizer A and fertilizer B, fertilizer Z, these three groups are independent. These three groups are independent. Now suppose we have A treatments level of single factor, right? So first we have to understand what this factor and levels are, right? So now let's say our factor, for example, fertilizers, right? So let's say our factor is the effect of fertilizer on plant growth. Otherwise, if I want to take a practical example, the factor can be for example, teaching style or teaching method. Teaching method is our factor. Now we have to perform a research in order to find out the effect of teaching method on the student's performance in the examination. Let's assume in this scenario. So here the teaching method can be different methods, right? So the teachers may adapt to different methodologies for teaching. So let's say the first one is online mode and the other one is physical mode, or we can say in person. And the other one is hybrid, right? So some classes are conducted online, and for practicals they have to come to the school or university, right? So here these three are called levels, right? So the divisions of our independent variable, right? So now here this will be our independent variable. So basically when I demonstrate my, right, so when I just draw a graph, so this will be my x-axis. Here this in x-axis we will denote teaching method. So we have three types of teaching method. So the first one is online, the other one is in person, and the third one is hybrid, right? So now in the y-axis we are going to denote our or label our dependent variable. So here our dependent variable may be the marks of students, right? So marks of students, right? So here this will be marks of our students, right? So now if I consider 10 people for online mode and 10 people for in-person mode and 10 pupils for hybrid mode, now after conducting an exam I can just label their marks, right? So here I have to have 10 data points, and here also I have to have 10 data points. Likewise I will mark, and I can find out the mean of these 10 students, and I can mark using a different color, right? So this is for our convenience. And here also we can mark the mean of these 10 students and the marks of these 10 students, and the overall mean can be calculated by adding these three and dividing by 3, right? So that will be y double dot bar, right? Otherwise, in other way we have to add all the data points and divide by the total number of data points, right? So now this is the summation of marks, the total marks of all 30 students divided by 30 will be our y double dot bar, right? So this can be denoted in the graph in the y-axis, and we can interpret our findings, right? So here this is the basic idea. This will be actually required when we do some complex examples. So having this in our mind, we will move to our topic. Now here let's say we have A treatments, right? So the treatments or levels, right? So this is a treatment, online is a treatment, in person is a treatment, and hybrid is a treatment. But the single factor means now the marks of the students depend on the teaching method. Let's assume only the teaching method influence the marks of the student. So this is a single factor. Now if we have more than one factor, that will be a multiple factor. And for example, let's say okay, so so our dependent variable is marks of students. Now these marks of students depend on let's say only the teaching method. So the teaching method, we have three treatments, or we can say three levels, and the marks of the students can be learning style of the students also. Let's say learning style of students. So the learning style means like self-study and group discussion, right? So here this factor, so this is a factor, this factor has two levels, and this factor has three levels, right? So I hope you can understand the differences between this treatment and factor. So here suppose we have A treatments. Let me erase all these things and create some space. Right, so here suppose we have A treatments, right? So the number of treatments is A, and under each treatment we have n number of observations, right? So here number of treatments, here you can see number of treatments can be number of groups. This can be denoted using I, and we have 1, 2, 3 up to A number of treatments, and under each group we have n number of observations, right? So for example, here if you take online, in person, and hybrid, right? So these three are now here A is 3, right? A is 3 because we have only 3 treatments, and we have taken 10 students, and we are just taking their marks, right? So let's say 70, 85, 90, 24, and so on. So we have 10 observations, and for these 10 students also we are taking their marks, and hybrid also we are taking their marks. So here this n is equal to now 10. N is equal to now 10, right? So you hope you can understand this. So here we have two models, right? So now we will discuss mean model, and the other one is our effect model. And under effect model, right? So here we might have statistical models. So the statistical models may be mean models and effect model. So there is no difference. Actually, the difference is here Yij. This is our independent variable. I don't know if you can see my eraser. Yeah. So this is Yij is equal to mu I plus epsilon, right? So here we do not have any effect, right? So only the independent variable is our mean. So that's why we call it as mean model. And here in effect model we will have treatment effect in addition to the mean, right? So that's why this is called effect model, right? So under effect model we have two types. The first one is random effect model, and the other one is fixed effect model. So we will see what these two models are later. Now we will try to understand these two different models. Here Yij is the ijth observation, right? So why ij mean the observation for the ith treatment and jth observation, right, or jth replicate, right? So we can call these 10 students under online can replicates also, right? So we can call these 10 students under coming under online mode as replicates, right? So here yij means the observation for ith treatment and jth replicate or jth observation, whatever. Now mu I is the mean for the ith vector, right? So ith vector means, if I consider, so right, for example here, this is my first mean, this is my second mean, this is my third mean, right? So this mu I is the ith mean, right? Ith mean the mean of the ith vector. So this is the first vector, this is the second vector, and this is the third vector, right? Okay, so here we have to find out these actually this should be level, right? So if it is level, then fine, right? So this is the first level, this is the second level, and this is the third level, because we have only one vector. We have already told that this is single vector, right? So here mu I is the mean of the ith level. Ith level mean here online, independent, and hybrid. Okay, and epsilon ij is the random error component, and assume that epsilon ij follows normal distribution with mu is equal to 0 and sigma squared, right, for all I comma j. So here this is the main assumption of our error term in a statistical model. So we have some assumptions for error term in statistical model. The first one is the error term is normally distributed, and in normal distribution the parameters are mu and sigma squared. So here the mu is 0, so we just mention it as mu is equal to 0, right? So the mean of the error term is equal to 0 with a constant variance, right? So we know that this is called homoscedasticity, which means the variance is constant over a period of independent variable, right? So here this is a constant variance. So this is just assumption for this what do you call error term, right? So now we can tell expected value of yij, right? So expected value of yij is nothing but the mean of all observation, right? So yij is the each and every individual data points that we have in our list. So expected value is nothing but mean, average of all the data points, right? So if you have 30, for example, in this example we have 30 marks, the marks of 30 students. So we have to get the mean, right? So we have to add all of them and divide by 30. So that will be equal to mu I. Okay, mu I, ith vector, right? So this is actually, this should be mu I, not mu I, this is mu, right? So that will be our grand mean, that will be our grand mean. So here, okay, so expected value of yij is equal to mu. Now we will just, okay, so this is overall mu, right? Mu is nothing but we can call this as y double dot bar. Okay, so y double dot bar means, now okay, so we will just draw the sample from a population. So this is the population mean, and this is the overall mean of our sample. So that should be approximately equal to our population mean also, right? So this is what we are going to just consider here. So otherwise, anyways, we can tell this mu is the overall mean, that is the mean of all the data points that we have collected from the population. That's not a matter. Now our mu I means the mean of the ith level, right? So you have to understand what all these terms represent. So this is the mean of ith level, and this is our overall mean, and this is the treatment effect, right? So this is the ith treatment effect. So each treatment will have an effect in our mu. So mu I is equal to mu plus our tau I. So this tau I may be negative or positive. So if it is negative, this will be negative, but here we consider only the magnitude. Here we consider the magnitude along with the sign. If it is negative, it will be subtracted from the overall mean, and if it is positive, it will be simply added. So now okay, so far we have discussed about our mean model. Now we will come to our effect model, right? So here you can see mu I plus epsilon ij, right? So here you can see yij is equal to mu I plus epsilon ij, right? So here we consider only the mean of every treatment, but here we will include the effect also. But when we include the treatment effect, we have to partition the mu I as mu plus tau I, right? So this is basically what you have to know, right? So let me explain it clearly. Mu I is equal to mu plus tau I, right? So mu I is the ith treatment, ith level mu, and this is the overall mu, and this is the effect of that particular level, right? So if I just substitute mu plus tau I instead of this mu I will get the effect model, right? So basically this effect model is derived from our mean model by substituting mu plus tau I instead of this mu I, right? So here I is equal to 1 to a and j is equal to 1 to n. So here where mu is the overall mean that I explained already and common to all treatments, right? So this is very important. Here this mu is common to all treatments. How did we find this mu? Now mu is equal to summation of mu I divided by a, right? So this is also very important, right? So now for example, as I told you already, here a is equal to 3. Here a is equal to 3. In the example that I explained using this teaching method, our n is equal to 10, a is equal to 3, right? So now if I add, okay, now we can find the mean of this online mode, I can find the mean of this in-person mode, and I can find the mean of hybrid mode also. So if I add these 3 and divide by 3, that will give me the overall mean, right? So here this is how we have to calculate this overall mean. I is equal to 1 to a mu I divided by a, right? So this is overall mean. Here tau I is the ith treatment effect, right? So this is a parameter unique to the ith treatment, right? So this is unique to the ith treatment, which means if it is mu 1, that is corresponding to the first treatment. If it is mu if it is mu 10, that is corresponding to the 10th treatment, right? So if it is mu I, that is corresponding to the ith treatment. So this is unique. For each and every treatment, we will have different mu I and tau I, but mu is common for all these treatments. Okay, right. Now moving to the next point, both models are linear statistical model, right? Why? Because there is no square or anything. So these both models mean this mean model and effect model are linear statistical model. That the response variable yia is the linear function, right? So linear function, they are not quadratic functions of the model parameters. We do not have any mu squared or something like that, so that's why we call this as a linear function. So though both models are useful, the effect model is more widely used, right? More widely encountered, right? So even though we have mean model and effect model, we don't use this mean model. We will basically widely be using this effect model, right? So this is what this sentence says. both are one way or single way vector ANOVA model, right? So one way, they are not two way or two way ANOVA, they are just one way simple ANOVA models, where we will be comparing our F values or P values. The experimental design should be complete randomized design. So in our previous semester also we have studied about this what do you call the designs of experiments. They are complete randomized design. We call this as CRD, RCBD, which stands for randomized complete block design, right? So RCBD, and finally we studied LSD. In addition to that, we will study some more experimental designs in this advanced experimental design course. Okay, right? So the experimental design should be CRD. So in CRD, all the now what is the condition? For example, if you have 20 people. Now we assume that all these 20 people are having the same feature, right? So they okay, for example, if I take 20 people from a classroom, I assume that all are male or all are female. There is no gender variation and there is no variation, right? So all the treatments or the experimental units are homogeneous environment, right? Okay. And now we know that this is the major assumptions of this error term that is normally distributed. Okay, so I have just inserted here the main assumptions of the error term in statistical model. We have a lot of assumptions, but we will just consider these three. Now the error term is normally distributed. The mean of the error term is 0, right? Because if you add all the error term, ultimately you should get 0. And 0 divided by the number of error terms that we have, again it will be 0, right? So that's what it says. And homoscedasticity, the variance of the error term is constant across all levels of independent variable, right? So that is what so for example, I already told you sigma squared is a constant value due to this homoscedasticity property, right? Okay. Now here, since our error term is normally distributed, what can we tell about our data points? So now our data point is also normally distributed, but here you have to observe this sigma squared and this sigma squared are common for both error and our data points, the constant variance, but the mu is equal to mu plus tau I, right? Because for each and every for example, if you have for example, for online, this is the normal distribution, this is the normal distribution. Now we assume equal variances for all groups. That is one of the assumption for CRD method. Here equal variances, that's why we put sigma squared, and the same variance will apply for the error term also. But here this is mu I, the median is mu, the mean is mu 1 here, this is mu 2, this is mu 3. So if you have a number of observation, that will be mu a, right? So mu a, right? So I started from 1 to a, right? So that's why I generally put mu plus tau I, but mu is common. Why? That is the common, overall mean plus that treatment effect, right? So this is basically, otherwise I can write this way also. Yij follows normal distribution with mean mu I, comma sigma squared. So this mu I, instead of this mu I have just written this mu plus tau I. That's all. So now moving to the fixed effect model. As I told you, we have two types of fixed effect models. Already models we classified into mean model and effect model. We always use this effect model. Now under effect model we have two types. The first one is fixed effect model and the other one is random effect model. So in fixed effect model, that's what we are going to discuss under this topic. But a random effect model is also there. But since we are going to construct this ANOVA table, we will be focusing on F value. In fixed effect model only we will compare F value, but in random effect model, we will have to compare this Wahl's chi-square test, but we are not going to talk about this for now. We will focus on fixed effect model, right? We will just focus on fixed effect models. Here Yij is equal to mu plus tau I epsilon ij. As you all know, I is the number of treatments and j is the number of observations under each treatment. I'm sorry, treatment or level, right? So all are same, right? All are same. All the 8 treatments or levels we can say, but factor is different. Factor is different, but treatments and levels are the same, right? So factor is the teaching method, and the treatments or the levels are the online, hybrid, and in person. Are specifically chosen by the experimenter, and our inference is the assumption that we are going to make regarding our population. Here we will actually perform this hypothesis testing. Will apply only to the a number of treatments, and it cannot be extended to similar treatments that were not explicitly analyzed, right? So we will just take the right. So here in fixed effect model, we will specifically choose it. But here in random effect model, as the name suggests, we will pick the experiments or treatments randomly from the population. So that's why we are going to use chi-squared here. But here we will just construct our ANOVA table and come to a conclusion for our hypothesis testing. Now you can see here the statistical method. The statistical model for both fixed effect model and random effect model are same. Here Yij is equal to mu plus tau I plus epsilon ij. Here the number of treatments is a random sample from a large population of treatments. Here the inference is the assumption that we are going to make about the population could be extended to all treatments in the population of treatments. Since we are taking randomly, if we take any number, because we are going to give equal chance to all the treatments, right? So for example, if you have capital N number of treatments, from that we are going to take only a number of treatments. So since we are giving equal chances for all treatments in the population, here the inference could be extended to all the treatment. It can be applied for all the treatments. That's the effect. But here in fixed effect model, there is a bias because the experimenter will influence in selecting the treatments. Okay. Now here tau I is a random variable. Thus the particular tau I is not important, but we test the hypothesis about the variance, right? So here you can see this, the other name for this variant, the random effect model is variance components model. And here in variance component model, we have to test the hypothesis for variance. But here in fixed model, we will test the hypothesis for the model parameters. They are mu, tau I, and sigma squared. Basically, we will say mu is mu I is all mu I are same. For example, the mean of all the treatments are same. Here, this is what we will write, or we will test as hypothesis testing. But here in random effect model, we will check for variance of the treatment effects, right? So this is a completely different approach of this fixed effect model. So we are not going to talk about this right now. So moving to the fixed effect model, here as we discussed already, we have a number of treatments, and under each treatments we have n number of observations, right? So you can just see this flow chart or the data panel. Here the rows are the treatments, right? So the rows treatments and the columns are the the observations under each treatment, right? So the columns observations under each treatment. Okay. So here we have a number of treatments. Now Y11 means the first treatment, first observation, right? and after that we will have, okay, so just let me write, so y21, right? So this is the second treatment, first observation, and this is the ith treatment, first observation, this is the eighth treatment, first observation. Similarly, if I consider the first group or the first treatment here, first treatment, first observation, first treatment, second observation, and first treatment, nth observation, right? So similarly we can interpret all these data points. Now we have to find out the treatment total and column total, right? So column total and treatment total. So here the column total, this is column total, y1 dot, the first column total, we have to add all these data points. We have to add all these data points. So we can write it as summation yij. So let me write it over here in order to make you understand clearly. Y1 dot is equal to summation j is equal to 1 to n y1 j, right? So now j can take any value from 1 to n, right? So here this is y1 dot, and similarly we can write it for I dot also, right? So I dot means summation j is equal to 1 to n I j, right? I j, and for the last one I can write ya dot is equal to summation j is equal to 1 to n ya dot, right? So the eighth treatment, but we have to add all the, right? So if you put dot here, this represents the total. Here you have to understand this, because without understanding, don't just by heart it. Here this dot represents the total, right? So if it is coming first, that will be the total of the rows, and if it is coming second following letter or alphabet letter, we will call it as the total of columns, right? So here we take the total of column because before that dot we have a, right? And now we can find out the row total, right? So the row total, I can write this as y dot 1. So this is the first row total. Why? Because row total, so we have to add all these rows, but the first row is constant, so that's why I put 1 here, but dot means I have to add all these, right? So now y is equal to, I is equal to 1 to a. Why? Because we have items starting from 1 to a, and y I dot yi 1, right? So since this is the first one, right? So I can take any value from 1 to a, so that's why we have taken y1a, right? So this is how we can write. So the writing is very important, but in the examination and when we are performing data analysis, we can just add all these data points row wise. And here I can write this for y dot 2 is equal to summation I is equal to 1 to a why do I put I? Because I have to put I from 1 to a, and here this is 2, right? So here, because this is the second row, that's why we put 2 here. And here I can write y dot n is equal to summation I is equal to 1 to n, right? I is equal to 1 to n y I n, right? So here n, right? So nth row, right? So this is the second row, I put second, and this is nth row, so I put n. I is equal to 1 to n y I, because I have to add all these data points starting from 1 to a, I'm sorry, here a, right? So a, and here n. So this is how we can find out. And now If I add y double dot, that will be equal to summation I is equal to 1 to n, and summation j is equal to, I'm sorry, here this is 1 to a, 1 to n, yij. If I add all these data points, that will give you the grand total. So this can be called as grand total. And here we can find the average y1 dot bar, right? So this is the first treatment total, the average of the first treatment. So the total of the first treatment divided by n, because we have n number of observations, right? So we have to add all these and divide by n. It will give you the average of the first treatment. Similarly, we can find out this one also, right? Here this is yi dot bar is equal to yi dot divided by n, and likewise ya dot bar is equal to ya dot divided by n, which means we have to add all these and divide by n. Here also we have to add all these and divide by n. Okay, right. So now here this is how we have to find out the y double dot. So y double dot is equal to summation I is equal to 1 to a. We have to add all these, and here y double dot bar is the grand mean that can be divided by the total of all the observation divided by the number of observation. Here the number of total observation is a into n. An is the capital N, number of total observations, right? So here where n is equal to an. Now our hypothesis, as we already know, mu1 is equal to mu2 is equal to mu up to mu a, which means all treatment means are same. Okay, and here not H node, right? So the opposite of null hypothesis will be our alternative hypothesis, which means at least one treatment mean is different from the other treatments, right? So this is how we are going to write down the null and alternative hypothesis in words. That is, okay, mu I is not equal to mu I for at least one pair of I comma j, right? So in notation we can write this way also. And mu as the overall mean, mu is equal to, we have to add all the mean of all treatment means. We have I is equal to 1 to a, and divide by number of treatments by a in order to get this one. Okay, and we know that this can be, so this is what we know, and we are going to prove that the total, the treatment effect, the total of treatment effect should be equal to 0. Okay, right. So how we can do this is, now we know mu is equal to summation I is equal to 1 to a mu I divided by a, right? Now I know I is equal to 1 to a. Instead of this mu I can put mu plus tau I divided by a, right? So this is equal to summation mu divided by a plus summation tau I divided by a, right? So this is again mu, so this is again mu plus summation tau I divided by a. Here a is not equal to 0, so if it should be mu, here we have mu, so the entire fraction should be equal to 0. From this we can tell that summation of tau I is equal to 0. Okay, right. So here From this we can now modify our null hypothesis. Now we already know that mu1 is equal to mu2 is equal to up to mu a, right? So now mu1 can be written as mu plus tau1 is equal to mu plus tau2 up to mu plus tau a, right? So I can eliminate all these mu and we get tau1 is equal to tau2 is equal to tau a, right? So this will be equal to 0, because if the treatment total is equal to 0, we will say that all treatment effects are 0, right? So we can conclude, but now this is just our doubtful statement, right? We may doubt that all treatment, right? So otherwise that one to, okay, now you see here, if this the total of treatment effect should be equal to 0, the one situation all treatment effects are 0, otherwise tau1 is equal to minus tau2. So in that scenario also, so it is a combination or the mixture of negative and positive signs with the same magnitude. So in that case also it will be 0, right? So this is our null hypothesis. So this is how we are going to write it, right? So this is our H naught, and at least one tau I is not equal to 0, right? So this is how we are going to write down our null and alternative hypothesis. Now this is also very important, decomposition of the total sum of squares, right? So total sum of squares, okay, right? So here now we are going to partition our total sum of square into the addition of total sum of square error and sum of square treatment, right? So ultimately we have to derive this formula starting from here, right? So we know sum of square total, right? Sum of square total. So now for this data panel, I'm going to just going to represent the data panel into a Cartesian coordinate. Now let's say this is our treatments, right? Treatments, and these are our observations, right? So we have a number of treatments, 1, 2 up to a. Now in first treatment we have n observations, right? So I'm going to label them 1, 2, 3, 4 up to n observation, and similarly for second one also we have something like this, and for eighth treatment also we have something like this, n, right? So here it contains n number of observation, here it contains n number of observation, here it also contains n number of observations, right? Now I can find out the mean of this first treatment, second treatment, and similarly for all treatments, right? So let me use a different color for these. So let's say this is my y1 dot bar, and let's say this is my y2 dot bar, and let's say this is my ya dot bar, okay? And if I add all these three means and divide by a, that will give me my mu, right? So mu o y double dot bar, okay? So now in order to find the total sum of squares, what I have to do is, from all the data points I have to subtract this value and then square. Why? Because okay, now you see here, if this is greater it will be positive, if it is lesser it will be negative, but I want always positive, so that's why I am going to square it, right? So now sum of square total is equal to this minus y double dot, this minus y double dot, right? So here this is equal to summation I is equal to 1 to a, and j is equal to 1 to n, right? So this means I have to add all the data points, right? yij minus y double dot bar square. Okay. So this is our sum of square total. Now this should be partitioned to this and this. For this I am going to just make a slight modification in this equation. Okay. So here sum of square total is equal to summation I is equal to 1 to a, j is equal to 1 to n, yij minus y double dot bar holding squared. Now the modification is summation I is equal to 1 to a, summation j is equal to 1 to n. I am going to just subtract and add yi dot bar, right? Yi dot bar means that is the ith treatment mean, right? So yij minus yi dot bar plus yi dot bar plus minus y double dot bar holding square. Now you know a plus b holding squared is equal to a squared plus b squared plus 2ab, right? So now here I am going to consider this portion as a and this portion as b. So this can be written as summation I is equal to 1 to a, summation j is equal to 1 to n, yij minus yi dot bar holding squared plus summation I is equal to 1 to a, summation j is equal to 1 to n, yi dot bar minus y double dot bar holding squared plus 2 into summation yij minus yi dot bar into again here this one yi dot minus y double dot bar holding square. Okay, this is I is equal to 1 to a and this is j is equal to 1 to n. Now if I consider only this portion, let me copy this. Now I have to show that this portion is equal to 0, right? So here okay. So now if I consider this one, my objective is to make sure or is to show that this is equal to 0. So now if you look at this one, for this summation, this is an independent, this is a constant because this expression is independent of this index because we do not have any j here. So I can take this out of this summation. So I can write this as 2 into summation I is equal to 1 to a yij minus y double dot bar into summation j is equal to 1 to n yij minus yi dot bar. Okay, right. Now if you look at this one here yij minus y double dot bar. Now I can write this portion as, now this is one summation and this is another summation. Now these two summations are multiplied, right? So now I am going to just consider only this one, right? So let me highlight it. I am going to consider only this one. right? So this means here you can see summation, for example summation x plus c can be written as summation x plus summation c, right? So now I'm going to apply this one here, 2 into summation I is equal to 1 to a yij minus y, okay, minus summation y double dot bar into this portion is coming here, right? Now 2 into this is equal to, now if you have ij, right? So if you, for example, summation, so if you add all these treatment means, it will be giving I'm sorry, here I have to consider this one, right? I'm going to consider this one. Okay, I'm sorry. So I just took this expression out, so it should have been written like this. Okay, so I made a mistake here. Right? So now it can be written as 2 into summation I is equal to 1 to a yi dot minus y double dot bar into summation j is equal to 1 to n yi dot minus y double dot bar square, right? Now here if you consider this one, now this is a summation, this is another summation. So now here 3 numbers are multiplied because it will ultimately give you a number. This also will give you a number. So now if I just consider this one, right, not this one. So if you consider this one, this can be written as according to this, I can write this as 2 into summation I is equal to 1 to a yi dot minus y double dot bar into, now I'm going to write this one, right? So let me use a different color. So here summation j is equal to 1 to n yi dot minus y double dot bar, y I dot bar, here I dot bar, okay, don't confuse, here I dot bar, this is what I have written over here, right? So okay, so I'm going to split this summation, right? So yi dot minus summation yi dot bar. Now yi dot means treatment total is added, right? So here this will give me now you know yi dot bar is equal to summation yi dot divided by n, right? So yi dot summation of this is n y bar I dot y bar, right, minus n y I dot bar. Why? Because here j is equal to 1 to n, here this is independent, so this is a constant for this summation, so n times this, and here for this I can write n into I dot bar, so here this is equal to 0. If this is equal to 0, the entire expression is equal to 0, right? So from this I can write this becomes 0, right? So if this becomes 0, I can write this as, so I can just eliminate this, I don't want to write this down because that becomes 0, right? I have proved that separately. Here now I can write this as sum of square total is equal to, now this is our sum of square error right? Sum of square error, and this is our sum of square treatment. Sum of square treatment. Why do I say this is equal to sum of square treatment? Now from the treatment total, right? So here these are the mean of treatment. If you subtract this, if you subtract y, okay, now this grain mean from each and every mean of the treatments, it will give you the sum of square treatment, right? The variance square of treatment. And now this is sum of square error. Why? Because from each and every point you divide this you subtract this. Okay, now from this you subtract this, and for each and every data point you do this, right? So now you can see here this is okay, but now for this one I can slightly modify this. I can slightly modify this in order to obtain this expression. If you look at this one here, for this summation, this is a constant, because here the index is j, but here we do not have any j, right? So for this is a constant, so this can be written as plus, this can be, instead of this one only I am going to write it, right? So only for this one, summation I is equal to 1 to a n times, right? So that n is a constant, so I can take it out, n into yi dot bar minus y double dot bar. So this is what we have derived here. So this is the sum of square error, and this is the sum of square treatment. I hope you have understood how to partition this sum of square total to sum of square error and sum of square treatment, right? So you can see here, this is the description of these terms, and yeah, sum of square treatment is the sum of square of difference between the treatment averages and grain average between treatments, right? So we can say between treatments and within treatments, right? Between treatment means, let's say these are the treatments, so these are between treatments, and between these we have within treatment, right? So within treatment points we have variation. That variation is called within treatment, and between treatment means between the groups, Since total number of n is total number of observations, sum of square total has, now for degrees of freedom, right? So now if I write down this one, SS total is equal to SS error, okay, SS treatment plus SS error. Here an minus 1 is the degrees of freedom. Here, since we have a number of treatments, a minus 1 is the degrees of freedom, and here since we have n replicates, n minus 1 will be the error degrees of freedom. Okay. So you can see here, as there are a level SS treatment, a minus 1 degrees of freedom, and since we have n replicates, here this n minus 1 will be the degrees of freedom for error. Okay. Now I'm sorry. Here, okay. So now the total some degrees of freedom is an minus 1, and treatment degrees of freedom is a minus 1. Now degrees of freedom of this one, okay, it's not n minus 1. So let me take it as x. So x is equal to an minus 1 minus a minus 1. That is equal to an minus 1 minus a plus 1. So if I take n out, a minus 1, right? So n into a minus 1 is the degrees of freedom of this error, right? So here a into n minus 1 is the degrees of freedom of error, So an minus a, this can be again written as n minus a, right? So n minus a, or n into a minus 1, right? Anyways. Okay, now this is the variance of error, right? So variance of error can be written as, so now we will understand what we have done here. Right, so here SI square, variance of error, can be written as summation j is equal to 1 to n yi minus yi dot bar holding square divided by n minus 1. Okay, right. So now this is what we have to obtain, but using the original or parent equation for SI squared, right? So now SI squared is equal to, as we already know, that is no, okay, so right, so this is our variance of our error SI squared. Okay, so what we have to do is, if I go to that page, I can easily understand. So now if you want to find out the sum of square of error from each and every data point, that is yij, we have to subtract this n square, right? So this can be written as, and for all n we have to do it, right? So for all n we have to do it. So this can be written as summation j is equal to 1 to n yij minus yi dot bar holding square. Okay, and the degrees of freedom is n minus 1 for this, right? Okay, now what I will do is, I will just multiply this n minus 1 and this n minus 1. Now SI squared n minus 1 divided by n minus 1, this will not change the value, is equal to summation j is equal to 1 to n yij minus yi dot, here dot is there, bar holding square divided by n minus 1. Now I will take summation, right? So I am going to take summation I is equal to 1 to a, right? Actually this is our error, but we have taken only for one group, right? So only for one group, because we have considered j is equal to 1 to n, means we have considered only one group, one particular group, but this could be done for all the treatments also. That's why we are taking summation here again 1 to a for all treatments, but this is for all the observations or replicates. Now okay, so you see here, this is for all the replicates in one treatment, but now what we have to do, the same procedure should be carried out for all the treatments. That's why we are taking I is equal to 1 to a. Again I can take for this entire expression, I can take, for this entire expression I can take summation I is equal to 1 to a, right? Now if I expand this will become summation I is equal to 1 to a si squared is equal to, now summation I is equal to 1 to a, summation j is equal to 1 to n y I j minus y I dot bar holding square divided by summation, because this summation is for this denominator also, n minus 1 I is equal to 1 to a. Now if you add I is equal to 1 to a for n, now okay, now if I consider this one, this denominator, summation I is equal to 1 to a, n minus 1 can be written as summation I is equal to 1 to a n minus summation 1. So now this is nothing but n, and I is equal to 1 to a, 1 means that is n minus a. So now this becomes summation I is equal to 1 to a, summation j is equal to 1 to n yij minus yi dot bar holding square divided by n minus a. Okay, right. So now this is nothing but sum of square error, right? Sum of square error divided by n minus a. Sum of square divided by n minus a is equal to this is what we have already written, is equal to this, and this is equal to this what we have written over here, because this is this, right? So from this we can tell SSE divided by NA is the mean square error, because this is actually mean square error, right? So this is actually mean square error, because we have taken the average of all the error points, because already we consider only the error, the total the what do you call this SI squared, yeah. Now this is mean square error, right? So this is mean square error, because we have taken the average of all the data points, that will be the standard deviation of error. So from this we can tell MSE, mean square error, is nothing but the variance, right? So this is variance, by the way, right? Because variance of error, so this is nothing but variance of error, right? So now MSE, this is our MSE, and this is sum of square error n minus a is the MSE, right? So this is how we write MSE, and mean square error, if you divide sum of square error by its degrees of freedom, it will give you MSE, and this is also MSE, and MSE is nothing but sigma square, that is the variance, the estimated variance of the error term. Okay, right. So from this we will discuss in the next video. So bye.